Welcome to intersecting polar curves. So for example, let's go ahead and find the points of intersection of r equals cosine theta and r equals cosine of 2 theta. So let's first just go ahead and draw these. So r equals cosine of theta is just a circle of diameter 1 sitting on the x-axis that goes through the origin. R equals cosine of 2 theta looks a bit like a flower. So let's do r equals cosine 2 theta in a different color. And we wind up getting this sort of 4-petaled flower shape. So looking at the curves, it appears that we have essentially 4 points of intersection. And again, looking at the curve, it looks like we have 4 points of intersection. At the curves, we have 4 points of intersection. Right, so we can go about solving this similar to what we do with x and y. We can go ahead and set our two equations equal to each other. So if we set the equations equal to each other, we have cosine of theta is equal to r is equal to cosine of 2 theta. So we are looking at cosine of theta is equal to cosine of 2 theta, or cosine of theta is equal to 2 cosine squared of theta minus 1. That's our double angle formula for cosine. This gives us that 2 cosine squared theta minus cosine theta minus 1 equals 0. We can factor this as 2 cosine of theta plus 1 times cosine of theta minus 1 is equal to 0. And we get, therefore, that cosine of theta is equal to negative 1/2, or cosine of theta is equal to 1. Cosine of theta equaling negative 1/2 corresponds to theta equaling 2 pi over 3 or 4 pi over 3 for our first time around the unit circle. Cosine theta equals 1 corresponds to theta equaling 0 or 2 pi. Okay, so it looks like, oh, we have 4 points, right? But of course, that 0 and 2 pi are the same. Point. If we go back to our graphs, our theta equaling 2 pi over 3 actually corresponds to the point of intersection in the fourth quadrant. The circle r equals cosine theta. 2 pi over 3 flips over into that fourth quadrant. So this point is our theta equals 2 pi over 3. That point of intersection in the first quadrant actually is on the second time around. That is our theta equals 4 pi over 3. So again, that intersection in the first quadrant occurs on the second time around the circle. We have our point out at 1, 0, or traditional, or at 0, 1, 0. Radius 1 equals 0. This corresponds to theta equals 0 or 2 pi. Right. We have yet to hit the origin. So again, note the intersection in the first quadrant occurs on the second lap around the circle. The intersection at the origin was not found because the different graphs are in at the origin at different angles. So essentially what we've seen here is that the intersection of a polar curve really depends on what you define an intersection to be. So the intersection points of the curves depends on the definition of intersection. So if they must occur at the same value of theta, then we get one answer. Right, sort of what we found, right? So theta could be 2 pi over 3 theta could be 0, 2 pi over 3, or 4 pi over 3. And again, at 2 pi if you wanted to include it, right? If they do not have to occur, if we're just looking at the same x, y coordinates, then we would also include the origin. This whole thing can get complicated because, of course, when we are dealing with trig functions, our function will just cycle through itself. We also run into the issue of we can land on the same point using using an opposite angle due to a negative r value. So some complications we run into. Whenever r is 0, or at the origin, it doesn't matter the angle. Right, the angle doesn't matter. Similarly, if r is negative, for one function, then the opposite angle will land us on the same point. So I guess I should say not if r is negative. I should say if r1 is negative r2, or r2 is negative r1, right? Then the opposite angles so essentially theta 2 equals theta 1 plus pi, or theta 1 minus pi, will land us on the same xy coordinate. So again, it really depends on your definition of what it means to be intersecting. So if you're simply looking for where the curves cross visually, then that will be one thing. If you're looking for where they're actually at the same point at the same angle theta, then that's a completely different concept. So this is the basics. We found where they crossed at a specific angle theta simply by setting the two functions equal to each other. Next week, we will look into calculus, and then it will definitely make a difference whether we're talking about just intersecting XY coordinates or intersecting at like the same r theta.